Hello all and welcome to this video. I know it says part 2 in the title, but we're up to part 3, I think, of using matrices for transformations. So we're continuing on. Our learning intention is still the same, where we use matrices to represent and apply transformations. The big change here, though, is we're now moving towards where applying the transformations represented as a function, as a matrix, to functions. So we're applying these, instead of just to a single coordinate, we're applying them to functions. So in a sense, we're now moving towards a general form. By the end of all of this, I'll probably end up having to split this section into 2 videos as well. But an example of success is we have a transformation T where we're mapping from R squared to R squared is defined by that series of transformation matrix. What is the image of the curve y equals 1 on x under this transformation? So this is our transformations that we're going to apply to y equals 1 on x. Some of this notation looks a little bit funky. We'll come back to it, but quickly, this is just saying we're on 2-dimensional Cartesian plane, mapping to 2-dimensional Cartesian plane. That's all that R squared to R squared is, so no need to freak out about that. So let's get going. So we had previously, we were applying a transformation like this to a coordinate. This time, though, we're going to apply this transformation matrix to y equals 3x minus 2. Now, the same system still applies. We still have our new x is going to equal to our old, equal to some form of transformation matrix applied to x, and then sometimes we might plus b, or sometimes we call it c, which that b or c is our translations. But the A is a 2x2 matrix, and that's what we're dealing with at the moment. It's just a 2x2 dilation reflection matrix. Previously, this x here has been actual numbers. It may have been like 2, 3, or something like that. Where, like I said, we're moving towards a general sense now, where instead of applying it to 2 and 3, we're just applying it to x and y. Okay? So we can still perform the matrix multiplication and find new coordinates, and going back to dash terminology, we have x dash and y dash is going to be equal to some matrix A 2x2 multiplied by our old coordinates. And that gives us some general equations that we can then do substitution in to the equation. So let's get on with it. As I said, this is x dash is equal to A times by x. So we just put the things in this, and like I said, we're just keeping this as x and y instead of an actual coordinate numbers. We do the matrix multiplication as normal, and we end up getting, let's think of it, x dash y dash is equal to 3x and negative y. So we can read this now horizontally across, and we can see that x dash needs to be equal to 3x, and y dash is equal to negative y. This is now giving us equations that are very similar to dash methods we've looked at before. We just want to rearrange to make x and y the subject. So we want to get x by itself and y by itself. Why do we want to get that? Well, that's what's in our old equation. We have an old x and old y. We want to substitute in to get something that has now x dash and y dash, our new values, which is what we do. Over here, we're subbing these 2 bits into the equation that we're asked to transform. And then it's just a matter of rearranging to get it so that it looks like y dash equals something. So that's using the dash / substitution method. We can still do this with inspection and replacement. And I certainly suggest, again, inspection is generally quicker. If you're really tied to the dash method, that's completely fine. But if we want to have a look at it, inspection, because it's that little bit more efficient. So it's the same problem. Transformation defined by the matrix A, blah. Find the equation of the image of the graph of the linear equation y equals 3x minus 2 under this transformation. Well, this is just a dilation and translation matrix that we can look at. And if we know the patterns, we can read off. And we think of this as affecting X coords, okay, and this is affecting Y coords, and then interpret from there using inspection and remembering the patterns. So if my X coordinates are going to be multiplied by 3, that means the X coordinates are changing. That means I'm actually dilating by a factor of 3 from the Y-axis. If the X variables are being multiplied by 3, that means they're effectively, if we think of center graph, they're being multiplied by 3, that means they're being pushed out by 3, factor of 3. What are we stretching away from? Well, we're being stretched away from the Y-axis. 2, we can see that the Y coordinates being negative, being made negative. So if the Y coordinates are being made negative, that means we're actually flipping or reflecting about the X-axis. So we can also see that we are reflecting about the X-axis. Okay. And since we know now, just reading straight off what the two transformations are, knowing the transformations, we can use our replacement rules that come along with inspection. So if we're dilating by a factor of 3 from the Y-axis, that means we need to Go. Now my PowerPoint's going again. We need to replace X with X on 3, and we also need to replace Y with negative Y. So let's do that straight away. So we're going to replace Y with negative Y, so we get negative Y is equal to 3. We're going to replace X on 3 minus 2, and so we get negative Y is equal to the 3, and the 3 cancel, so we get X minus 2. Come over here, we just want to bring the negative across, so Y is equal to negative X plus 2, because we need to, actually I'll show you the extra step just to be clear, is we're bringing the negative across and it's affecting the whole right hand side, so we can then say Y is equal to negative X plus 2, or we sometimes don't like to write the negative first, so we get 2 minus X, which is exactly the same as what we got on the previous slide. Y is equal to 2 minus X if we're rearranging. Right here, so that's using inspection, just recognizing the patterns, knowing what the reflection, what the transformations mean, or the numbers inside the matrix, what transformations actually mean, and then we can use that to do our replacements. Couple of things about using inspection, okay, is that if we use translations, we need to read the translations as they are. There's no changing the signs in reading what the translations are. So if we're used to looking at an equation of a graph and we read our H value and we switch the sign of the H, we don't need to do that at all here. Let's just read, this is what we're transforming. We're transforming the X by plus 5 and we're transforming the Y by negative 2 in this case. You still have to do the correct replacement, so where you do put the signs as you do the replacement. So since we're translating to the right by positive 5, we need to replace X with X minus 5, and then we also need to replace Y with Y plus 2. And so that's where that, remembering our replacement rules and how they flip around. So that's what's done here. We replace Y with Y plus 2, and we replaced X with X minus 5 to this equation. That's what we've done. Being really careful that this X minus 5 we're putting in brackets, okay, because the 2 is affecting all of X, and that's what we're replacing X, and then just simplifying down. Matrices reflected through the line Y equals X, and just to be clear again, what that is, is we're flipping, instead of reflecting about the X-axis or the Y-axis, we're actually reflecting over that diagonal line, Y equals X, which is the same as what happens when we find the inverse of a function, is it actually gets flipped over that Y equals X line. So this trick of switching the Y and the X values is really handy to find inverse, which is what we do when we actually find the inverse. That means if that is the case, if that's one of the transformations applied, the rest of our numbers actually end up in this odd diagonal, or the secondary diagonal, which we've nicknamed it. So we've got a 2 and a 3 here, but it's not in the usual top left or the bottom right. What does this mean? Well, what this actually means is, because the numbers are there in that secondary diagonal, we have a reflection about the line y equals x. So to do that transformation, via inspection, recognizing it, is the first thing you need to do, okay, is swap the y and x's in the equation. So wherever we started with y is equal to 2x minus 3, we're still using the same equation. The very first thing we do is we need to switch the y and the x value. Sorry, just my kitten's jumped up. There she is. So we switch them, which is that. And then what we can do is actually now read the matrix in a regular fashion. So the top number, we can now actually read it as if it was sitting in there, and the bottom number, we can read it as sitting in there. Because by flipping the x and y in the equation, we're effectively flipping the matrix as well. And now we can just read, I am dilating by the x coordinates are being multiplied by 3, the y coordinates are being multiplied by 2, so that's a dilation of 3 from the y-axis and a dilation of 2 from the x-axis. Think of what the replacements are that you need to do, and go from there. So just apply the inspection method as regular. You don't have to worry about this whole flipping and the x and y's changing if you're doing it by the dash method, because when you do the dash method and the numbers are here and here, when you do that matrix multiplication and get these numbers, the x and y's automatically swap and all the transformations follow along. So as a dash method, there's no issues there. Just do the matrix multiplication and you'll be fine. One last thing is to be, and we talked about this in class today, is to be really careful of recognizing, especially if you're doing inspection, and actually the matrix operations, is you've got to be really careful of the brackets. Okay? So if we can see here that these brackets, which I've now highlighted in red, that means if you do inspection, you have to apply the transformations first, and then you're going to come over and apply these ones. As you can see, again, we're on the secondary diagonal, so you're going to apply these first, the translations, then you're going to, looking at this, you switch x and y if you're doing inspection. Okay, you're going to switch x and y, and then once you've done that, then you can apply the rest of the dilations and reflections. Here just shows the process of doing the matrix multiplications and then reading top line across, which gives us this, and then reading the bottom line across, recognizing that this is still here, so x dash and y dash. Read them across, rearrange to make x and y the subject, and then do your substitutions over here. You get eventual final equation. If you did that via inspection, you'll get the exact same thing. And I will stop there, and we'll hopefully start with this in class. I'll give you a couple of minutes to have a crack at it yourself and see how we go. If you have any questions, please ask.